You will notice here that I have a list of the things that we're going to cover today. And right at the top of that list, we have what is a vector. So a vector, ladies and gentlemen, is going to be just a directed line segment. So let's say we have a point there. We have a point 5, 5. And that right there represents a single point. 5, 5. This is a point that has both an x and a y coordinate. Now, a vector can be described as a directed line segment. And so an arrow from the origin to this point represents a vector. And to denote that that's a vector, we're going to use these vector brackets. So there's a difference between using parentheses and these vector brackets. The parentheses mean that it's a point, and these brackets mean that it is representing a vector. And it's going to have a comma b. We're going to be using a and b, a for the x and b for the y coordinate of this. This is what we call component form of a vector. Now a vector has two things. It has direction and it has magnitude. So direction, which is usually going to be in the form of an angle, and then it also has magnitude, which simply means the length of the vector, or of the line segment that is representing the vector. So this arrow right here is in what we call its standard representation. So far we've gone over what is a vector, component form of a vector, which is this, and a standard representation. So standard representation means that the vector begins at the origin. And when I say begin, I mean that it's going to extend from the origin to some other point. Now there is one vector that does not extend, and that is called the zero vector. And the zero vector has no direction and has a magnitude equal to 0. So a zero vector would literally be just there. So far we've gone over what is a vector, the component form of a vector, a standard representation of a vector, and a zero vector. Now, if there is a standard representation of a vector, there has to be a non-standard representation of a vector, I guess. So let me go ahead and draw another vector right here. Now you notice that this vector is not in standard representation because it does not begin at the origin and thus extend outwards. Instead, it's in the second quadrant, and it kind of begins at x is 6 and y is 1, and then it ends over here. Let's plot these points right here. So this is 6, 1, and this is going to be 1, 6. Now the question I have for you is, are these vectors equivalent? Are they equal? And the answer may surprise you. The answer is actually going to be yes. And the reason for that is because even though this vector, the green one right here, is not lined up so that it begins at the origin, it technically still has the same direction and it also has the same magnitude. If I were to take this and I were to slide it down, it would actually line up exactly with my original vector. So for that reason, we can say that they're equivalent. But on paper, you're not going to have the option to grab that vector and slide it down. There has to be a way to prove that these are equivalent. And the way you prove that is by using the head minus the tail rule. So let's talk about head minus tail. You could pretend that this green vector is sort of like a snake. And as a snake slithers, its tail is left behind from where it started, and its head is in the direction that it's going. So when you talk about the head minus the tail, is you're taking this second point and you're subtracting the first point. The formula for head minus tail is x2 minus x1 comma y2 minus y1. So let's actually go ahead and subtract these to see if we can find its component form. We're going to take my x2, which is -1, and we're going to subtract my x1, which is -6. So I have -1 minus a -6, which actually ends up giving me a +5. And then we have y2, which is 6, minus y1, which is a +1, and we also end up getting a 5. And we see that this is actually equivalent to my original vector. And like I said, if they are equivalent, it must mean that we are able to take it, slide it, and line it up exactly. So that's really all you need to know about your head minus your tail rule. Let's talk about magnitude for a second. So magnitude. If I'm looking at this vector, and I'm asking myself, okay, what is the magnitude? I'm actually asking myself, what is the length of this line right here? And the cool thing about vectors is that no matter where they end up, you can always form a 90-degree angle using the x-axis, sort of like we did when we were working on reference angles. We can create a 90-degree angle here, which turns this whole thing, including the vector, into a right triangle. And again, you can do this with any vector. So knowing that this side is 5, and that this side is also 5, and that this whole thing is a right triangle, we can actually use the Pythagorean Theorem to find this side of the triangle, which is going to be the length of my vector, which is going to be its magnitude. Now, my Pythagorean Theorem states that if I have a squared plus b squared, then that will equal c squared. This is going to be my hypotenuse right here. So 5 squared plus 5 squared is going to be equal to, and actually, the proper notation for magnitude is the absolute value of your vector. Now, you don't say absolute value of your vector, but instead you call that the magnitude of vector v. So right here, this means magnitude. So to continue, we're going to go ahead and say, well, 25 plus 25 has to be equal to 50. And 50 is equal to the magnitude of my vector squared. So to find the magnitude of my vector, I go ahead and take the square root of 50. Now, we have to go ahead and simplify 50. We're going to simplify this into 25 times 2, which is going to give me 5 times 5. And this can now turn into 5 times the square root of 2. And so this would be the magnitude of my vector. Now there is a formula that you can use just in case you don't want to go through the trouble of drawing your vector and then using the Pythagorean theorem. Let's pretend for a second that this vector is still back here. And let's also say that we can't move this vector and get its component form. There's actually a formula that we can use for magnitude. And the formula is this. Magnitude is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And I want you guys to notice something, that this is actually your Pythagorean theorem, but in a single equation. So there's no steps in this, it's just everything is laid out in the equation for you. So we already labeled my x2, y2, x1, and y1. So all we really need to do is plug it in. So x2 was negative 1 minus a negative 6. And notice how we already did this. We already found the component form of my vector. So I can actually breeze through this. And this is going to be 6 minus 1. We're going to add them together after we square them. So this will give me 5 squared plus 5 squared, which is 25 plus 25. And then we take the square root of the whole thing, which is the square root of 50, which again can be separated out into 25 times 2, which is 5 times 5, which gives me the square root, or 5 times the square root of 2. And so that's all there is to magnitude. It really is just the length of this vector. And you can do it this way. If, for example, that they don't give you a drawing and you don't feel like drawing it, you can just go ahead and do it mathematically, or you can do it this way and actually draw your triangle and look and see that what you're really looking for is your hypotenuse. And you can use Pythagorean theorem to find it. A squared plus b squared is equal to c squared. Let's talk about vector addition and scalar multiplication. So vector addition. Let's say we have two vectors. We're going to call this vector u, and it's going to be u1 comma u2. And we want to go ahead and add it to vector v, which is v1 comma v2. Now the formula for adding these is going to be very, very simple. All I'm going to do is say that u plus v is equal to u1 plus v1 comma u2 plus v2. So I'm going to take each of these component form vectors, go ahead and add them together, and they will each give me a new component form, if that makes sense. Now, this is a little bit hard to see on paper, but it becomes very, very easy to see once you can see it in a drawing. So let's say I have vector v in orange, and I have vector u in purple. Now, adding these two vectors together is a simple matter of taking them and attaching them from end to end. So for example, I can take this vector right here and attach it to the end of the first vector, which is then going to give me this line right here. And the new resulting vector will be from the very start, from the origin, all the way to the top of wherever that vector ends. Or the bottom. It could go any which way. So this, right here in red, is going to be the answer to your vector. Now let's go ahead and prove it. Let's go ahead and put this one back where it was. And let's go ahead and move this off screen for now. So if I look at these two vectors that I have, I know that this smaller purple one, this has u is equal to negative 3 comma positive 3. And v, it's 5 comma 7. So according to this formula that I have here, I should get my new vector by simply adding this and this and this and this. So negative 5 plus, so negative 3 plus 5 gives me 2, and 3 plus 7 gives me 10. So my new resulting vector should be 2, 10. Now if I go ahead and put this red line segment back, I see that it actually does end up at 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this red vector is 2, 10. Now a couple things that I want you guys to note is that it actually does not matter when it comes to addition which vector you add to which one. You could take the purple and stick it at the end of the orange, or you could do the exact opposite. Leave the purple where it is and take the orange vector and stick it to the end of the purple one. And it will not make a difference. Both of these should end up at the same point. And you can see that by the way that I'm sliding these around and moving them around. Now, I also mentioned that you can always find the magnitude of a vector by drawing a right triangle. That includes when you add them. So even if you have vector addition going on, you can always create a right triangle. This will be 2, this will be 10, and you can now find the magnitude of this vector by either doing the formula for magnitude. By the way, this is distance formula, just in case you hadn't recognized yet. Or you could use Pythagorean Theorem. 2 squared plus 10 squared. So you can set up Pythagorean Theorem. 2 squared plus 10 squared is equal to your magnitude squared. I don't know if we should use v because we already have a v, so let's go ahead and say, let's call this vector x. So we're going to find the magnitude of vector x squared. Now, we go ahead and say, well, this is 4 plus 100 is equal to the magnitude of vector x squared. This is 104, and then we can take the square root of both sides to get the square root of 104. Now, the square root of 104 can actually be simplified. Let's see by what. Well, 104 is 2 times 52, and 52 is 2 times 26, and 26 divided by 2 times 13, and it seems that this is as far as we can go. 4 times the square root of 26. And this would be the magnitude of your vector. And we can check that off the list, vector addition. So scalar multiplication is actually pretty interesting, because what you're going to do is you're going to actually either make this vector have a larger magnitude or a smaller one. And the way you go ahead and do that is by actually saying, well, let's say we have vector, let's call this vector p. And vector p has a component form of 1, 2, 1, 2, 3. And scalar multiplication simply asks you to multiply the whole vector by a certain number. Let's say 3. So 3 times vector p. And all you're going to do is distribute that 3 in here. So 2 times 3 will give you 6, and 3 times 3 will give you 9. And so now you have, we're going to call this p prime, of 6, 9. And what you're going to notice is that what you did was just sort of extend the vector by 1, 2, 3. Because now we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is now vector P prime. And notice how it's simply a combination of these three vectors put together, because of course you multiplied by 3. So this is scalar multiplication, and you can either multiply it to make it longer, or you can also multiply it to make it shorter. If you go ahead and multiply this by 1/2, then you get 1 comma, when you distribute this, of course, you get 1 comma 1.5. And in this case, what you did was you ended up making this shorter by about half. And so there you go. That's scalar multiplication in a nutshell. It's very, very simple. And the only thing that you have to worry about is distributing and making sure that you count the negatives, just in case. So now we have gone over vector addition, and we have gone over scalar multiplication. Let's go over unit vectors and resolving a vector. Let's go over unit vectors. The word unit basically means 1. If you know Spanish, uni is a lot like uno, which of course means 1 in Spanish. So a unit vector is actually a vector with a magnitude equal to 1. So you can have vectors with different magnitudes, but when you go ahead and have a vector in a certain direction, for example, you can actually go ahead and say, okay, that's going to be a unit vector in a direction of, let's say, 30 degrees, or whatever the case may be. So let's actually go over an example. Let's say we have this vector right here, and we want to know exactly where this vector would end up if it had a magnitude of 1. We want to know the unit vector of this vector. So once again, we want to find the unit vector in the direction of, let's call this vector v. In the direction of v. Now, there are a couple formulas that we can use. A unit vector, which I'm going to describe as u, so u is a vector with a magnitude equal to 1. U is equal to vector v divided by the magnitude of that vector, which is equal to 1 divided by the magnitude of the vector times the vector. Both of these mean the exact same thing. It's only that I factored out the v there. So how is this actually going to help us? Well, let's say that we have unit vector, or that we have this vector right here, which is negative 1, 2, 3, 4, 5, 6, negative 6, comma, positive 2. A unit vector in the direction of v is simply going to be this vector divided by its magnitude. So the first step that we have to do is we have to find the magnitude of this. And we can do that one of two ways. I'm going to opt for the Pythagorean Theorem. This is going to be 2. This is going to be 6. So we have 2 squared plus 6 squared, which is 4 plus 36, which is equal to 40. Now, to find my v, because this is v squared, I need to go ahead and square root 40, take the square root of 40. So I'm going to take the square root of 40, which gives me 4 times 10, and this will give me 2 times 5. And so the only thing that I can take out of here is the 4, so it's going to be the square root of 4 times the square root of 10, which is 2 square root of 10. So since this is my magnitude of the vector, to find an actual value for my component form of a unit vector, I go ahead and take negative 6 divided by 2 times the square root of 10, comma 2 divided by 2 times the square root of 10. Now, why am I doing this again? Because that's what my formula tells me to do. It tells me to take my vector v, which is right here, and divide it by my magnitude, which I just found using the Pythagorean theorem. So this is actually going to be the unit. This is actually going to be a unit vector in the direction of vector v. Now, this is important because sometimes we just want the magnitude of everything to be 1, like when we are using the unit circle. There's that word again, unit circle, unit vectors. So these are going to be important and they're going to correlate later on. But for right now, what you need to know is that this is going to help us find basically the angle of, this is going to help us find the coordinates of any angle on the unit circle. So to continue this, if we actually wanted to graph it, we could pull up a calculator like Wolfram Alpha and say negative 6 divided by 2 times the square root of 10 we should probably put parentheses here. There we go. Our decimal approximation is negative 0.948. And then we can also say 2 divided by that, same. And the decimal approximation is 3.16. So 9.5 and 3.1 or 3.2 is going to be the unit vector. So if we go ahead and draw that, we're going to erase this right here. Negative 9.5 and 3.2 should be just about there. And of course, if we draw a vector in that direction, it should be the same vector, just with, again, a magnitude of 1. Let's go over really quickly what a standard unit vector is. So there are 2 standard unit vectors, I and j. And I is the vector 1, 0, and j is the vector 0, 1. As standard unit vectors, they are always going to follow either the y-axis or the x-axis in the positive direction for exactly 1 unit. Now, how do these help us? Well, it turns out that every single vector can be written as an expression of both of these. For example, let's say that we have this vector right here. The question is, how many j's, how many i's does it take to make up this vector? And you could very easily just say, well, look at this. If I go up 1, 2, 3, 4, and 1, 2, then I could end up at this vector. So we're going to go ahead and copy 1, 2, 3, 4 J's. My bad, I guess it took one more. And then we copied 2 I's. We could represent this new vector as an expression in terms of the standard vectors. So if this vector v is equal to a comma b, which is then going to be equal to it's going to be a comma 0 plus 0 comma b. You see, we're separating both the a value and the b value so that we can attribute those to I and j. We can say that this is going to be a times 1 comma 0, which that right there is I, and we're going to go ahead and say that this is plus b times 0 comma 1. See, we simply factored out the a and the b, and a can be this 1 comma 0, and b will be this. So now what we do is, well, if this was 1, 2, 1, 2, 3, 4, 5, this was vector 2 comma 5, we could say that this is in fact 1, 2, 3, 4, 5 i's and 1, 2, 2 j's. We can actually write this as vector v is equal to 2 times I plus 5 times j. And this is just another way of writing vectors using standard unit vectors. Now finally, we are coming back to working with angles. So this right here is resolving a vector. Now, a vector can be given to you in component form, a comma b, but it can also be given to you with two simple directives, which is direction and magnitude. So I could tell you where the vector is going to end up, but I could also tell you something like there's a vector v in the directional angle of 120 degrees with a magnitude equal to 8. And so because of this right here, we're actually going to need to find out, okay, well, what is my component form? Because I can't really plot 120 degrees here with a magnitude of 8. That's very, very difficult. So by using sine and cosine, we're actually going to be able to find the component form of this vector. So how do we aim to do that? The formula that we're going to have is v will be equal to the component form of the magnitude of your vector times the cosine of theta, comma, the magnitude of your vector times the sine of theta. Now notice that we have sine and cosine representing x and y once again. Also notice that your magnitude is going to multiply whatever this result is. In other words, if you wanted to find a unit vector, remember a unit vector which would show up on a unit circle, which will give you the inputs, or which would give you the coordinate points of the unit circle for this vector, this particular vector, in this particular angle, we could actually just ignore the magnitude, and it's simply going to be the cosine of theta, comma, the sine of theta. But that's only for unit vectors. if we're looking at regular vectors, we are going to need to multiply by the magnitude. But that's not a problem for us because we have been doing this for quite a while now. So what we're going to do is we're going to take everything that they've given us and simply plug it in. So this says 8 times the cosine of 120 degrees, comma, 8 times the sine of 120 degrees. What I would do at this point is I would go to a calculator and simply type that in. 8 times the cosine of 120 degrees. 8 times the cosine of 120 degrees gives me the value of -4. So this will be -4. And now I do the same thing for sine. This gives me 4 times the square root of 3 with a decimal approximation of 6.9. We can go ahead and use that, 6.9. And that can kind of be rounded up to 7. And so when we look at this, we say, okay, well, my vector is going to be 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7. So we know that it's going to be around there. And I guess now the only question we have to ask ourselves is, does this make sense? What I mean by that is, does this look like it's a magnitude of 8? And does this look like 120 degrees? Because if either of those don't make sense, then we might have done something wrong and we would have to redo it. But in this case, they do make sense. 120 degrees would be between 90 and 180, and this is just about 8 in length. So there we go. That is how we find the component form from direction and magnitude, directional angle and magnitude. Now the last thing that I want to go over is, how do you go the opposite way? How do you find directional angle and magnitude from the component form of a vector? So magnitude is pretty easy because magnitude we've already shown how to find, but the directional angle, that one can be a little bit tough. So magnitude of, let's try a new problem. Let's say we have vector -2 and 3. So this is vector v is -2, 3. And we want to find two things. We want to find the magnitude and we want to find the angle. So to find the magnitude, we're simply going to use Pythagorean Theorem. This is 3, this is 2. 2 squared plus 3 squared. This gives me 4 plus 9, which is equal to 13. So my magnitude would actually be the square root of 13, which is pretty simple. But now to find my angle, well, let's think about this. If v is -2, 3, and we can also write this as the absolute value of the cosine of theta, comma, the absolute value times the sine of theta, then we can use this relationship to find my theta. In other words, -2 has to be equal to my magnitude, which is square root of 13 times the cosine of theta. So what I'm going to do is I'm going to divide by the square root of 13 on both sides. And then I am going to go ahead and take the inverse cosine of both of these sides. So I'm going to take the inverse cosine of this. That way I can find my theta by itself. Now that's a little bit hard to do, so you're going to need a calculator for it. But you can go ahead and write the arc cosine of -2 divided by the square root of 13. And the answer is going to be 123.7 degrees. Now, how do you know whether this is correct or not? Because I can guarantee you that if I did the same thing on the other side, it's going to give me a different answer. So let's try it with sine. So this gives me 123.7 degrees. So 123.7. Let's see what happens when I try the same thing with sine. It would basically be the exact same thing except for the 3. So I'm looking for the inverse sine of 3 over the square root of 13. So now it's a positive 3 over the square root of 13, and we're using inverse sine. And inverse sine is giving me 56.31. So check out what happened. If you guys remember from our lesson on inverse trigonometric functions, each of these functions has a domain and a range that they have to stay in. Cosines happens to be the first and the second quadrant. So all of this is in the realm of cosine. And sine is in the realm of the fourth quadrant and the first quadrant. So in this case, there is no possible way that sine would have gotten you the correct answer. So what you have to do in this case is you have to go with cosine, 127.3 degrees. Now you can also be sure, because like I said before, this is 90 degrees, this is 180. It would not make sense for this to be 56.3? 56.3, because 56.3 would be right here. And so for that reason, this has to be 123.7. And with that, we have basically covered everything that you guys need to know about vectors. This is just a little quick introduction. Let me know if you guys have questions.